Okay, so now let's take this this quantization rule that we found from this discussion. That is the quantization of the wavelength of the matter wave, the electron matter wave that corresponds to the classical orbital radii, classical orbits of the electron about the nucleus, and let's combine that with de Broglie's hypothesis, because after all, this hypothesis was known at the time. Okay, so we have from the previous view graph, we have n lambda is equal to 2 pi r. N is again an integer, and r is the classical orbital radius. And the de Broglie hypothesis gives this relationship for between the wavelength of the matter wave and its momentum. So it's just the Planck's constant divided by its momentum, h over p. And for a classic non-relativistic particle, I should say, the momentum is just approximately mv. Okay, so now we have n, the integer, times h over mv is equal to 2 pi r. Okay, and so if we rearrange this, we find that mvr is equal to n, the integer, times h over 2 pi, Planck's constant divided by 2 pi, which we know is the h bar. H bar is Planck's constant divided by 2 pi. And so now we have this relationship here, which is important. Now, some of you may recognize what MVR is, okay? That's the angular momentum, the classical angular momentum. And just to show that, so the angular momentum L, the vector, is defined to be the cross product of the position vector of a particle relative to some point, r, times its momentum vector, okay? And for, again, for a non-relativistic particle, then the momentum is just mv, and so we have r cross mv. Now, for a at least for the classical orbits, okay, the classical orbitals, then the velocity of the electron is always perpendicular to the position vector relative to the nucleus, and so r and v are perpendicular, and so the absolute value, the magnitude of the momentum L, is equal to just mvr. Okay, and so what we find is that, again, from this argument, that the angular momentum is quantized. L is equal to n times h bar, and this is in fact one of obviously Bohr's hypotheses, and just kind of shows the plausibility of that hypothesis by relating the matter wave properties of the electron, the wave properties of the electron, and how when you do that, how the quantization of angular momentum kind of just falls out. Okay, so angular momentum is quantized. Another thing to notice is that since the orbitals are standing waves, okay, and what I mean by that is that they're not propagating. Remember, this is sort of the picture kind of the electron wave, as if you just break up the orbital and spread it out in the circumference, and this wave is a stationary wave. That is the nodes, the antinodes fluctuate up and down, so they, like any wave, it fluctuates in time, but it's stationary in the sense that it's not traveling anywhere. Okay, and so sort of by definition, standing waves are stationary states, and so it's at least plausible that these sort of wave-like orbitals don't radiate. Now, all this logic is somewhat flawed. It establishes the plausibility of Bohr's hypotheses, but it's somewhat flawed because, for example, it neglects the radial component of the standing wave. So we've only talked about the angular component of the we've basically assumed that the electron wave is confined to the circumference of an orbit, but in fact it also has a radial component. That is, it can move towards and away from the nucleus, and that's not taken into account. And there are some other small flaws, but at least it establishes the plausibility. Now let's see where this can take us in terms of calculating energies.